Okay, in our next unit of study, we're going to look at some effects that relate to the non-ideality of gases. Most of these effects are going to have to do with the intermolecular forces, because of course in ideal gases, the molecules don't interact in any way. But of course, real gases do interact, and that leads to some interesting effects. So that's just highlighting what we just said. Now, polar molecules, of course, will interact very strongly, and water being a polar molecule has a really strong interaction with other water molecules. But even for nonpolar, say like oxygen, you get a fairly weak but nonetheless present interaction between the two molecules. Oxygen's diatomic, so here's a terrible picture of an oxygen molecule. And what'll happen is that a temporary shift in the electron cloud will make this end a little bit more negative and this end a little bit more positive. And that can induce a temporary shift in this electron cloud, where the electrons would be attracted to this end, and then you'll get a weak attraction between those two molecules. Now, that's not a very strong effect, but it is nonetheless present. It needs to be present, otherwise oxygen would never turn into a liquid. And of course, if you get it cold enough, oxygen does liquefy. So these weak forces of attraction are ultimately responsible for phase changes, and that's one of the things we'll look at in this unit. Now, these weak attractive forces, we can represent them by drawing potential wells. So this is just a graph of potential energy versus separation distance. And this graph will be important when we discuss refrigeration and the Joule-Thomson effect. So we'll come back and draw that a little later. But you can see that when the molecules are here, they're pretty happy. That is the minimum potential energy. And then if the molecules are going faster, then they will separate. And as they get further apart, they will gain potential energy and lose kinetic energy. So they'll start to slow down as a result of those intermolecular forces, as a result of the attractive forces. This is a lot like a gravity well. I mean, if you shoot a rock up from the surface of the Earth, as it separates from the rock, it gains potential energy and loses kinetic energy. So gas molecules, although the attraction is a lot weaker, behave the same way. Now, because of these attractive forces, these intermolecular forces, internal energy no longer depends on the temperature. It will also depend on, say, the volume. Because as you decrease the volume, you're decreasing the separation distance, and therefore changing the amount of energy. Now, this is going to affect our calculus because we can no longer write du dt, the exact differential. Instead, we have to use partial derivatives because u now depends on a couple of variables. And here's a beautiful diagram from a text by Atkins that shows that. So this is now an internal energy. It's no longer a line, it's now a surface, and it depends in the plane on both temperature and volume. So if you start off here with a certain amount of energy, then your change in internal energy is going to depend on whether the volume's changing, and as we project down here, we see this was a constant volume process, or whether the temperature's changing, and as we project down here into the plane, we see that this was a temperature change process. Now, there's something known as the multivariate chain rule, which says the differential or the change in a function is how much it changes in the x direction times delta x, plus how much it's changing in the y direction times delta y, plus how much it changes in the z direction times delta z, plus etc. And that also works in reverse. So if you've got a statement, a differential of some function, and it's f dx plus g dy, whatever is in front of the dx, that must be a partial derivative of the function with respect to x. So we're just comparing these two, and we're saying that whatever is in front of the dx term is actually a partial derivative of this function. Whatever is in front of the dy is the partial of the function with respect to y. So, for internal energy, now let's get really specific. The differential of internal energy, well, it depends on volume and on temperature. So it's going to be the partial derivative of internal energy with respect to volume times however much volume changes, plus the partial derivative of internal energy with respect to temperature times however much temperature changes. So what that looks like on our surface, here is our starting point, and then here is the internal energy change at constant volume times the little bit of dV. So here, if we call this A, then this is A right here, right? That's the change of internal energy along a line of constant volume. And then here is the slope, partially u with respect to t in this direction on the surface, times dt. And so you end up at the final. This is the final internal energy, and this then will be delta U. So I guess this is U initial, we could call it. And so what you've got right here is delta U, or du, in the limit of very, very small deltas. And so that was the volume change, and then this was the little bit of temperature change, dt. So our internal energy as a result of this process changed from this point on the surface to this point on the surface. Now, we above just wrote partial of u with respect to v, but you see it's often possible, it is possible to parameterize the internal energy in terms of other variables too, not just volume and temperature. You could also do pressure, you could also do entropy. So it's customary for us to indicate what the other variable is that we're parameterizing. So we'll write it as a little t there to indicate that we're dealing with, first of all, u as a function of volume and temperature, and then its rate of change with respect to volume at constant temperature. So rate of change with respect to volume at a constant temperature. Now, in this first example, you say, well, that really doesn't seem to be necessary, but you'll see very shortly that these partial derivatives get quite complicated, and therefore it does become a really helpful thing to have. And let's just get straight into it. Here's the first law in differential form, and now let's substitute our expression for du, which was partial of u with respect to v dv, plus partial of u with respect to t dt, and this was at constant temperature, and this was at constant volume. Now that's du, so that's got to be dq plus dw. Let's look at a couple of processes. First of all, constant volume. At constant volume, a little bit of thermal energy, dq is ncv dt. And the work done, well, work is minus pdv, but if the volume's constant, then that's just going to be 0. So if we substitute in, constant volume, I guess I should write dv as 0 here. So we're going to have, we substitute in for dq ncv dt. We substitute in for work, well, I guess we could put it in there, but then we're going to make it 0. This dv conveniently is 0. And so we can see here there's a relationship between the constant volume specific heat capacity and the rate at which internal energy changes with temperature. So that's a good conclusion to draw. So for CV, we can say that NCV is the rate of change of internal energy with respect to temperature at constant volume. Now, if you were to sort of make this a U here, if you were to cross multiply that, you could kind of get back to, the ideal gas relationship that we had, which was the internal energy was just directly proportional to the temperature, depended only on the temperature, and then the coefficient of proportionality was N times CV. So this certainly would agree for an ideal gas. But this is true in all cases. This is true for ideal and non-ideal gases. So that was looking at constant volume. Now let's deal with constant pressure. So with constant pressure, dq is ncp dt. We again substitute in two the first law. And so what we get is dq, and then dw is minus p dv. And so if we rearrange that and solve for dq, it'll be, well, first we can write it as du plus p dv. And then for du, we can substitute what we had previously, which was partial of u with respect to v. Oh boy, I gotta separate my u's and my v's better. dv plus partial of u with respect to t dt, so that's du, and then we have plus pdv. And so we can factor two dv terms. So I've got partial of u with respect to v, that's at constant temperature, plus pressure. All of that is times dv. And then we've got partial of u with respect to t at constant volume, dt. So I'm not putting in that with respect to constant v and with respect to constant t here, but I will put it in at the end result. If it makes you feel better, you can put it in absolutely everywhere. I just find that's a bit cumbersome and time consuming. Okay, so we want to work at constant pressure, not at constant volume or temperature. So it means we're going to have to reparameterize this equation a little bit. We're going to have to put in something for dv. Well, so here's the equation copied again. Volume is a function of pressure and temperature. So for its differential, we can say that dv is dv dt, partial derivative with respect to temperature, plus its partial derivative with respect to pressure, dp. And so where we had dv, we're going to substitute this in. So when I substitute that in there, this is what results. So I get this bracket times partial v with respect to t dt. There's that. Then I had this partial u with respect to d dt sticking around. But then I've got to have this bracket multiplied by partial v with respect to p dp. Now these are both dt terms, so I gather them together and put them in this big bracket. And then, of course, we've got partial of u with respect to v plus p. That's a u. Times partial of v with respect to p dp. Okay, so we want the constant pressure specific heat, and since dq is ncp dt, we rearrange and solve that for ncp, we get dq dt, but really that's like partial of q with respect to t at constant pressure, and the partial of q with respect to t should be exactly this term in the expansion. Remember, by the chain rule, that this should be partial q with respect to t dt, and this should be partial q with respect to p times dp. So using the sort of inverse multivariate chain rule, we say, aha, this is the rate at which q changes with temperature at constant pressure. And that's exactly what NCP is. So we arrive at this result. Now, this term here, this was at constant volume. This was at constant temperature. And this was dV dt at constant pressure, to put that all in. Because this term came from up here. We were expanding volume as a function of temperature and pressure. So this looks like quite a complicated result, but it is true for non-ideal gases. It works everywhere. Now we'll show in an assignment question that if you put in the ideal gas equation, that this gives us back the very simple relationship. First of all, for an ideal gas, U depends only on temperature, and that's your internal energy, and therefore that Cp minus Cv just works out to R again. So here's our result. You're going to show in an assignment that for an ideal gas, it gives us back something simple, but we're going to apply it to non-ideal gases, and one example that we'll do later is a van der Waals gas. So I guess the subtitle of this section could be bring out the partial derivatives, because we're now, when we deal with non-ideal gases and allow for the molecules to interact with each other, now internal energy not only depends on temperature, it also depends on volume. And we're going to see that all of our quantities can be parameterized in two other variables. So there's going to be a lot of partial derivatives in this section. So in class when we meet, we're going to spend a little time working on the chain rule to make sure we understand how to use it and what it's telling us. And we're then going to spend some time changing this equation into something a little bit more useful.